Hello everyone, welcome to the presentation of our paper, Novel Approach of Class Incremental Learning on Internet of Things Framework. My name is Swaraj Dube and I'm the lead presenter of this paper. First, let's talk about deep learning. For a long time, deep learning models have been trained statically. That is, a lot of data is gathered, after which a big deep learning model is trained on a powerful server using hardware accelerators such as GPUs. And once the model is trained, it is deployed into the real world where the model makes its predictions. Though this method has achieved great success, the main problem is that once a model is deployed in this manner, the model will not be able to learn from new data because such models have only been trained to make inferences after they have been deployed. In our paper, we talk about class incremental learning. So what is class incremental learning? It is the ability to learn new tasks over time, just like how humans do. A representation of this feature is shown in the figure on your screens right now. Models typically become more complex as they learn new tasks. As I mentioned about static deep learning, instead of training a model on a central server using large amounts of data, in edge computing, some of the processing that takes place on the cloud is moved to edge devices that are very close to the data source, as it can be seen from the figure on your screen. The reason for doing so is to reduce the dependency on the cloud. For example, Tesla manufactures many self-driving cars, but these vehicles do not send data to the cloud for processing. Otherwise, a delay can be caused, especially for such critical applications. Data in the real world keeps changing. For example, our faces change as we grow older, and a large amount of data is collected through IoT devices. So if no processing takes place on IoT devices and all of the data is transmitted to the cloud, this will require huge bandwidth and computational cost on the cloud. This is why we need IoT edge devices to tackle this problem of reducing the dependency on the cloud. And this is also why we need to start thinking about deep learning in an incremental learning context. As we already know that IoT devices collect large volumes of data, but now the question is whether all of the data collected is needed for learning. The reason why this question is important is because when we are dealing with data such as images which are high dimensional, then transmission of such kinds of data to the cloud can lead to an expensive transmission cost. This is why we must only select certain data from the collected data and only then make the transmission to the cloud in an attempt to reduce the computational load on the cloud and reduce the transmission cost. This, however, leads to another question, which is, will the incremental learning performance be affected if certain data is discarded at the IoT device? In our method, we use an i7 processor laptop with 8 GB RAM to emulate an edge device, and we use an NVIDIA K80 GPU on Google Cloud that emulates a cloud. We focus on an image classification problem. As data starts arriving from each class, we randomly discard a certain number of samples and forward propagate the remaining samples through the CNN feature extractor. Once we obtain the feature maps of such samples, we save them on the IoT device, and once we finish processing all samples from each class, we transmit all the features to the cloud via TCP/IP. However, we don't start training yet. We only start training when all the features from classes that belong to an incremental training round have been sent to the cloud. For example, training only starts once 10 classes have been sent to the cloud. On the cloud, SMOT is used to create a balanced dataset in case the number of samples per class are not the same. After training, we increase the number of neurons in the softmax layer to accommodate for learning new classes. After this, an acknowledgement message is sent to the IoT device indicating that the IoT device can start processing the next batch of images. Now, this is how we carry out incremental learning on the cloud. Each neuron in the final layer represents a class. Therefore, when new classes arrive, then the number of neurons in the softmax classification layer, which is the final layer in this figure, increases, and the weights associated with these neurons are randomly initialized. Now we carry out joint training. Joint training is the most common form of incremental learning, whereby the new samples are mixed with the old samples, and this concatenated dataset is trained on the updated model. CFAR 100 dataset contains 500 training images per class and 100 testing images per class. It can be seen that when we transmit only 300 samples to the cloud, the accuracies we obtain at every incremental training round is less than 2% as compared to the baseline. And when we transmit 400 samples to the cloud, then the accuracies at every incremental training round is less than 1% as compared to the baseline. Baseline refers to transmitting all samples to the cloud. The training time on the cloud also reduces significantly with respect to less training samples. The same observation can be seen here as well when using a different model and dataset. CUB200 has 200 classes but has a very small number of images per class. However, even in this case, when we discard 5% of the images in every class, the classification accuracies obtained are less than 2% compared to the baseline. To conclude this presentation, we can see from the results that not all of the data is needed for learning. Sending less samples to the cloud leads to a reduced transmission cost along with faster training time on the cloud. Another observation is that when dealing with data sets which have a high number of samples per class, the amount of data sampling that can be done is much larger as compared to performing data sampling on data sets with a small number of images per class. Most importantly, we saw that data sampling for incremental learning is able to retain incremental learning performance regardless of the model, dataset, and hyperparameters. We would like to stress that we do not present any novel data sampling algorithm. We simply show that yes, it is possible to discard certain number of samples from a training distribution and still retain incremental learning performance, which is why for future work, an algorithm should be developed to dynamically sample data from a given data distribution with respect to its size. And also, a novel loss function should be developed that can deal with continuously arriving imbalanced classes, because this will eliminate the need of oversampling on the cloud. Thank you very much.